Hi class, welcome to your lecture on power series. Now, in a second I'll talk about what power series are, but let's start with what the objectives are for this lecture. So the first thing I want to do is I want to understand the definition of what exactly a power series is. What we want to do is we want to find the radius and interval of convergence of a power series. All right, then we want to determine the endpoint convergence of a power series, and then the last thing we're going to do is differentiate and integrate a power series. Okay, so what exactly is a power series? So an important function here, f of x is equal to e to the x, all right, can be represented exactly by an infinite series called a power series. So for example, the power series representation of e to the x is e to the x is equal to 1 plus x squared over 2 factorial, x cubed over 3 factorial, dot, 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 to x sub n over n factorial, all right? And this is for each real number x. So it can be shown that an infinite series on the right converges to the number e to the x. So by definition here, if x is a variable, then the infinite series here, a sub n, x to the n from n is 0 to infinity, is called a power series. So more generally, an infinite series of this form here, where it's not just x to the n, but x minus c to the n, this right here is called a power series centered at c, where c is some constant. All right, so let's talk about some. So the following power series here, obviously, is centered at 0. Because if you look back here, it's x to the n power. A sub n is some constant, all right? So it's x to the 0 power, x to the first power, x squared, x cubed, so on. So that's a power series centered at 0. All right, this one here has x plus 1 to the n, and then you see 1, so that would be when x is 0, and so on, and so on, and so on. But now if you look back at our definition, let me go back, sorry. It's x minus c. So here I have x plus 1, so it'd be minus 1. So we say this power series is centered at -1. And here I have 1 over n, x to the minus 1 to the nth power. You can see right here, obviously, that it's just x minus c, and the c is 1, so this is just centered at 1. All right, let's talk about radius and interval of convergence. So a power series in x can be viewed as a function of this, all right, summation n is equal to 0 to infinity, a sub n, x minus c to the n power. Now the domain of this function f is a set of all x for which the power series converges. So of course every power series converges at its center, obviously, because like when you plug c in here for x, it's just equal to a sub 0 because everything else, c minus c, just goes away. All right, so that's easy. So c always lies in the center of the domain of f. Okay, so we have this theorem, 9.2, and it's to follow, or 9.20, states that the domain of a power series can take 3 basic forms: a single point, an interval centered at c, or an entire real number line, as you've seen below. So it can converge at a point, at an interval, or it can converge at all real numbers. Right? So the domain of this power series has these 3 basic forms. All right, so the convergence of a power series. So for a power series centered at c, precisely one of the following is true, not both, one. All right, the series converges only at c, so only at the center, or there exists a real number r which is greater than 0, such that the series converges absolutely for x minus c is less than that r number, and it diverges when x minus c is greater than that r number. All right, or the series converges absolutely for all x. All right, so single point, all real number lines, specifically when it converges or diverges then. So the number r there is the radius of convergence of the power series. So if the power series converges only at c, then the radius convergence is 0. If the power series converges for all x, then obviously the radius of convergence is r is equal to infinity. So the set of all values of x for which the series converges is that interval of convergence for a power series. All right, so let's find the radius of convergence for this one here. So I got the sum of n is equal to 0 to infinity, n factorial x to the n. All right, so for x is equal to 0, when you plug it in, all right, 0 raised to whatever power doesn't matter, it just equals 1. So what we're seeing here, for any fixed value of x, such that the absolute value of x is greater than 0, right, we're looking for that radius of convergence. So I'm going to let u sub n here be n factorial x to the n. And then I'm going to use this limit theorem here to figure out if it converges or diverges. So plugging in our limit here, you can see that this is just equal to the absolute value of x as n goes on the outside. Just by simplifying, the limit as n goes to infinity of n plus 1. That's equal to infinity. So therefore, by the ratio test, the series diverges, all right, for the absolute value of x greater than 0. So this one only converges at its center, 0. All right, so we can say here that the radius of convergence is r is equal to 0. Let's talk about endpoint convergence next. So for a power series whose radius of convergence is a finite number r, all right, theorem 9.2 says nothing about the convergence at the endpoints of the interval of convergence. So what happens is each endpoint must be tested separately for convergence or divergence. All right, so as a result, the interval of convergence of a power series can take any one of these 6 forms: single point, infinite, all real numbers, and then depending on the endpoint, if it's inclusive or not. All right, so let's find the interval of convergence of this. N is equal 1 to infinity of x sub n over n. So again, using that ratio test here, all right, I'll let you look through the algebra here, u of n plus 1 over u sub n. This is just going to simplify to this right here. And this just, again, converges, or the limit is the absolute value of x. So by the ratio test, the radius of convergence here is r is equal to 1, all right? So moreover, because a series is centered at 0, it converges in the interval from -1 to 1. This interval, however, is not necessarily the interval of convergence. All right, so to determine this, you must test for the convergence at each endpoint. So when x is equal to a 1, you obtain the divergent harmonic series, simplified as this: 1 plus 1/2 plus 1/3. So it diverges when x is equal to 1. When x is equal to -1, you obtain the convergent alternating harmonic series, however. So it converges when x is equal to -1. So the interval of convergence for this series is inclusive -1, 1, as shown in the figure here. All right, let's talk finally about differentiating and integration of a power series. So theorem 9.21, properties of functions defined by power series. So we have this function here, this power series function, has a radius of convergence r greater than 0. Then on that interval, the open interval, c minus r to r, c plus r, f is differentiable and therefore continuous. Moreover, the derivative and antiderivative of f are as follows. So here's the derivative. You can simply take the derivative. Here, over here, you can simply take the integral. So the radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. The intervals of convergence, however, may differ. Okay, so convergence, the radius of convergence is the same, but the intervals might not be. All right, so consider this function. All right, summation n is equal to 1 to infinity, x sub n over n. This is what it is. Let's find the interval of convergence for each of the following. So the integral, the general function, the derivative. So by theorem 9.2, you have when we're going to integrate this, or excuse me, when you take the derivative, this is just x to the n minus 1. So this is what the series looks like as you expand it out. And here, when you integrate this, it simply integrates to this right here, which is this function right here. So by the ratio test, you can show that each series has a radius of convergence r is equal to 1 here. Consider the interval, the open interval, -1 to 1, and you have the following. All right, so for the integral, this series right here, the summation of x n plus 1 divided by n times n plus 1, it has an interval of convergence at both endpoints. So this converges at x is equal to plus and minus 1, and its interval of convergence looks just like this. The general series, so here, the interval of convergence, it's inclusive of -1, but not 1, right? Because it converges for x is equal to 1 and diverges when x is 1. Right, so the interval of convergence looks like this. And then finally, the derivative here, this one here, it diverges for x is equal to plus or minus 1. And so its interval of convergence is open interval, -1 to 1, and it looks like this below.